Hey everyone, welcome back to another Explainer. Today, we're unpacking a fascinating research paper by Kyle McLean-Smith. And honestly, it proposes a pretty radical shift in how we think about quantum physics and geometry. We're looking at something called the cycloid logarithmic bridge. I know, right? Sounds like a mouthful, but don't worry, our focus today is super grounded. We're essentially going to bridge the gap between abstract one-dimensional geometry and our physical two-dimensional reality. And we're doing it to get away from those mathematical infinities that always seem to plague quantum electrodynamics. Okay, let's dive into this.
So here's our mental roadmap for today. 1. The magic of the cycloid. 2. The photon straight line limit. 3. Decoding the decay parameter. And 4. The rectangular area duality.
All right, Section 1, the magic of the cycloid, geometry in motion.
To kick things off, I want you to picture a really simple scenario. Ask yourself this fundamental physics question. What's the absolute fastest path between 2 points in a universe governed by a uniform force field? You know, like gravity. Your gut reaction probably screams that a straight line is the fastest route, right? Well, hold on to that thought for a second.
Because it turns out your intuition might actually be tricking you here. The real answer is a very specific curve called a cycloid, and this is due to something called the brachistochrome property. The cycloid is literally the trajectory of absolute fastest descent. If you try to force an artificial, straight-line shortcut, you actually just generate higher latency and more friction. The natural curve literally beats the straight line every single time. It's just a beautiful reminder that the universe kind of favors its own natural geometry over our artificial shortcuts.
But wait, the cycloid has another incredible trick up its sleeve. It's called the tautochrome property. Imagine you've got a bowl shaped like a cycloid. If you release a marble from the very top edge, and then you release another marble from just an inch above the bottom, guess what? They both hit the absolute bottom at the exact same time. The time to convergence is totally invariant to where you start. It doesn't matter what your initial displacement is on that slope. The duration to reach the minimum potential is exactly identical. It's almost like the curve has its own built-in, unchangeable metronome. Pretty wild, right?
Moving right along to Section 2, the photon straight line limit, pushing the curve to infinity.
Okay, so a cycloid is generated by tracing a point on a rolling circle. A standard one has a curved path driven by a circle with a finite radius. But let's push this to the extreme. Look at what happens in the photon limit. As this decay parameter, which we'll call d, approaches 1, the radius of that rolling circle grows infinitely large. And as it does, it smooths out completely into a flat, straight line. Think about it. A circle with an infinite radius has exactly 0 curvature. So why does this geometric morphing actually matter? Well, because it directly dictates physical reality. We already know from Fermat's principle of least time that photons, light particles, travel in straight lines in a vacuum. But this framework suggests something deeper. They aren't just choosing a straight line randomly. They travel that way because the straight line is the pure geometric limit of that cycloid brachistochrone we just talked about. The straight line isn't some separate isolated phenomenon. It is literally just the cycloid pushed to infinity.
The source material actually summarizes this beautifully. It states, photons are massless invariant constants executing pure geometry, distinct from unhalted floating point drift. I just love that phrasing. It frames light not just as a physical thing moving through space, but as an expression of pure, unbreakable mathematical law playing out perfectly across the universe.
All right, Section 3, decoding the decay parameter, extracting the geometric DNA. Now, what's really interesting about this next part is how we unpack the algebra. Let's bring this back to basics and ground it in a simple right triangle. We have an orthogonal leg A, which acts as our horizontal infrastructure base. Then we have leg B as the vertical governance rise, and finally, hypotenuse C. Now keep this in your head, because everything that follows is built right on top of this fundamental geometric foundation.
So let's look at how the paper defines an invariant decay parameter, our d. It starts off as the hypotenuse minus the vertical rise, all divided by the base. So that's c minus b divided by a. Now, by applying a difference of squares, by multiplying the whole thing by c plus b, we can eliminate the radical, and it gracefully simplifies straight down to a divided by c plus b. It's incredibly elegant. The complex fractional parts just perfectly cancel each other out.
But here is where the real magic happens. The author applies what's called data normalization by simply setting that horizontal infrastructure base, our leg A, to equal exactly 1, The math collapses into something absolutely stunning. If A is 1, our original equation for D just becomes C minus B.
And this brilliantly illustrates a core geometric truth. The paper provides a mathematical proof showing that when you calculate the half-angle tangent of our triangle, so tan theta over 2, it simplifies to exactly A over C plus B. This basically proves that our decay parameter D isn't just some random algebraic fraction. It is identically equal to the exact half-angled tangent of the right triangle. The algebra and the geometry are just perfectly seamlessly synced up.
Which brings us to our final part, Section 4, the rectangular area duality, bridging 1D to 2D space.
Let's take a look at the geometry of this coordinate system. The paper evaluates two distinct boundaries here. On one side, we have the total macro column area, which is defined algebraically as A 2B plus AD. Sitting directly next to it, just for contrast, is the much smaller capping block area, defined simply as AAD.
So here is our climactic breakthrough. Remember that data normalization will be set A to equal 1? Well, if we plug A equal 1 into that capping block area formula, AAD, it just becomes 1 times 1 times D. It quite literally just becomes D. And we just proved that D is the 1D ratio tan theta half. So what does this mean? By setting A to 1, the two-dimensional spatial area of that capping block becomes numerically identical to the one-dimensional math ratio. We've basically successfully bridged 1D scaling directly onto a 2D physical canvas.
Which leaves us with a pretty massive thought to chew on as we wrap up. If a simple one-dimensional mathematical ratio can perfectly map onto and completely define a physical two-dimensional spatial block, is the foundational layer of reality actually built on physical particles like we've always been taught? Or is the universe, at its absolute core, just an expression of pure invariant geometry, where the math actually is the matter? It is an incredible perspective on the building blocks of our reality, taking us all the way from a rolling curved cycloid straight down into the architectural code of space itself.